Let's start today's lecture. As I mentioned, we are going to continue talking about adversarial robustness. All right, so a brief recap of the stuff we covered in the previous lecture. So we talked about the formulation of adversarial robustness, and we talked about attacks, and then we talked about defenses. Right, so briefly speaking, in the attack problem, the goal is to craft an adversarial example X prime such that to maximize the classification loss of my model, let's say f theta of X prime, given the label, the true label that we wanna misclassify or samples against that label, subject to X prime to be within a threat model of X with a particular parameter, let's say rho. Right? So we mainly talked about LP threat models, where we, in LP threat model, we have basically X prime minus X, the LP norm of it is less or equal to rho, but there are some non-LP threat models that I'm going to talk about them in the next lecture. All right, so that's basically the attack problem, and we solve this approximately using gradient descent. In the defense, we introduce adversarial training. So instead of a regular ERM that minimizes the average training loss, again, we are going to minimize training loss, but not on training samples, on the worst perturbations of training samples. So I'm looking at the average training loss, but inside the expectation, I'm looking at the attack problem for each of my training samples. So basically, I have the attack problem, subject to basically the threat model that we consider. So that's called adversarial training, which is a pretty effective defense. One good thing about adversarial training is that it is not particular for a specific threat model like L2 or L infinity. So whatever threat model that you have here, you can include in your inner maximization constraint and robustify your model against that particular threat model. And we basically do alternating SGD to optimize theta and PGD to approximately solve the inner maximization problem. All right, so, but there are many other heuristic defenses, empirical defenses that have been proposed in the literature. I see a question. Phil, go ahead.
Are we going to talk about convergence of alternating GD?
That's that's a very good question. So as you can see, unlike the standard ERM that we have a single minimization, we have a min-max optimization problem, right? So it is not a regular optimization that we discussed in the first parts of the, this course. So I'm going to spend one lecture on just understanding min-max optimization, either in convex concave or non-convex non-concave setting later on, because min-max optimization is also, as you know, useful in GANs and other types of problems. So I'm going to spend one lecture about that. But roughly speaking, here you can imagine that here we do have a good convergence, at least approximately. So we'll be talking about that more in the future. Very good question. Okay, so as I mentioned, there are many other heuristic or empirical defenses. Heuristic or empirical defenses, and people are really clever. They, they propose different, ways to, defend the model. Maybe add like a coding or a discretization step at the beginning before you feed your X into your network, or maybe randomly change your network architecture. You add some stochasticity to your network and see if it increases the robustness of your model. Just to give you, I'm not going to go into the details of any of these empirical defenses, but just to give you a brief idea, in ICLR 2018, probably 6-7 such empirical defenses have been proposed and they basically show that these defenses further robustify models, classifiers, either on MNIST or on CFAR against different threat models like L2, L infinity. So they have reported pretty good numbers about them. All right, but in a follow-up paper, in a subsequent paper by Atali, Carlini, and Wegner, in ICML, I think 2019. So I think 2018 actually. So what they showed was that most of these empirical defenses, they fall into this category of gradient masking or obfuscated gradient. So they are not really robustifying the model. What they are doing is that they're making gradient computation to be more difficult for the attacker. And since most of these attack algorithms that we have here, they're based on gradient descent, right? So the core component of gradient descent is to be able to compute gradient of your loss function reliably. If you cannot compute the gradient reliably, then potentially those types of attacks, they are not going to succeed against these defenses. And that's why they reported good numbers in terms of robust accuracy of these defenses against those types of attacks. But the argument in this paper is that these obfuscated or masked gradients, they can provide actually a false sense of security, right? So obfuscated or masked gradients provide a false sense of security, right? So because you think that, okay, yeah, I did like these, quantizations or coding or randomizations, and, I, applied like a PGD attack or FGSM attack, and wow, my robustness is like 80%. But that's false. That's because, you have basically just made computation of the gradient more difficult. And given that information, the attacker can basically circumvent these types of, masked gradient defenses. So in other words, such defenses can be, I would even say, easily broken using what is called adaptive attacks. By adaptive attacks, we mean that we have already seen the defense and what defense is based on. So we try to basically have a tailored attack for that particular defense. All right, so that's basically the gist of this really, really nice paper. So I encourage all of you to read this paper, especially if you're working in adversarial robustness area. But briefly, they identified different sources of gradient obfuscation in the paper. So I'll just summarize that finding. So we have obfuscated gradients that can come from multiple sources. Sometimes these defenses, they use non-differentiable operators as a pre-processing of the inputs. In that case, you get like shattered gradients. For example, when you are using non-differentiable operators as pre-processing your input. So I'll show one example of that later on. Sometimes you have stochastic gradients. When, for example, when you're using a randomized network. For instance, you can say, oh, I'm going to drop out some nodes and edges, you know, in my forward path. So the gradient computation in the backward path would be stochastic. And you can have also exploding or vanishing gradients, especially if in a recursive way, you are basically using one network as the input to another network, so you can have vanishing or exploding gradients. Right, so these are, roughly speaking, some sources of gradient masking or obfuscated gradients that they have identified. So there are some very, I would say, trivial, but very intuitive ways. If you are working on a defense, sometimes you may unintentionally have a defense that masks the gradient or obfuscates the gradient, and that's why you see robustness, right? You know, sometimes you do it intentionally, and you shouldn't, because, you know, I'll, you know, explain these things can be get around quite easily. But sometimes you may do it unintentionally. You don't know you are, you know, obfuscating or masking the gradients in your defense, but at the end of the day, that's what you do, and that's the source of your robustness, and that's a false sense of robustness that you get. So there are some easy ways to somehow check if your defense is based on gradient masking. Right? So how can we identify obfuscated or mask gradients? So there are some very sensible checks that you can do. So one of them is this check that if you have a defense and then you try a one-step attack like FGSM, and it performs better than iterative attack like PGD, that should raise a question, right? So because, you know, this iterative attack is based on repeated estimation of the gradient, and if you're masking your gradient, in that case your performance may not be good. So if your one step is better than multiple step, then this is not good, right? That should raise a flag, and you should investigate your defense a little bit more carefully. If you have a black box attack where the attacker doesn't know the model parameters, and if it works better than the white box attack, when the attacker actually knows the model parameters, it has more information, then again, this is a red flag, right? So it shouldn't be the case. Maybe you're masking your gradient in the white box attacks, and the black box attacks that is not using that information is more successful. So that should alarm you. If you have unbounded attack budget, right? So your row is really large. If the success rate is not 100%, then again, that's a, you know, red flag, because if your attack is, you know, a budget is unbounded, then you can always break your defense. So that should alarm you. And finally, if increasing the attack budget does not increase the attack success rate, right? So in that case, doesn't increase the success rate, then that's also a red flag. Right? So by attack budget, I mean this row. which is the perturbation budget that you have in your optimization. So these are really sensible checks that if you are coming up with an empirical defense, you should definitely look into these aspects. If any of them happens to be the case, then perhaps you're doing gradient masking. So you shouldn't basically you should think a little bit harder about where the robustness, if you observe it empirically, is coming into into the picture. All right, so let me just pause and see if there are any questions. Okay, good. I'm really happy that you guys are answering each other's questions in the chat box. The question is, okay, now if we identify a defense that uses a mask gradient, how we can attack it? How to attack defenses using gradient masking? It is actually really easy to attack. Okay, by easy, there are implementation, details and stuff, but broadly speaking, it is not hard to break these types of defenses. Okay, so let's look at two examples. One example one. Let's say your defense is based on adding a non-differential operator to your input. Defense based on adding a non-differential operator. So in other words, let's say you have G, which is non-differentiable, perhaps non-smooth function, and then you feed that G of X to your classifier instead of just X. And this is basically your new classifier, right? So here G, they're non-differentiable, even non-smooth functions, but because you don't want to degrade your performance that much, so you usually define these non-differentiable, non-smooth functions to be, roughly speaking, your input or close to your input, because you don't want to completely destroy your input. And there are several defenses, example defenses, empirical defenses, using different non-differentiable, non-smooth operators, right? So how can we break this? Okay, so if you just apply PGD on this, it is a big issue because this function that you have here is non-differentiable. So the gradients won't be able to compute. So the idea is, in the attack, in the backward propagation for the attack, just use the identity function instead of your G. Just forget about G. In the backward propagation, whatever gradient you have up until G, just copy, before G. So ignore G. G is the identity function. And in fact, this really simple way to get around this completely removes any robustness gains that you would obtain by having such a non-differentiable operator. That's why I'm saying these are really simple defenses to break if you know what they're exactly doing. But if you don't know, and then you just apply PGD, you would say, oh, you get like 80%, 90% robustness, which is like a false robustness that you observe. Right, so let's look at another example. Let's say you have a stochastic defense. Let's say defense uses randomized classifier. Right, so you can, for instance, drop out some nodes, edges here and there. So this is going to lead to stochastic gradients or random gradients. then you really don't know which direction you should go when you are attacking such randomized classifiers, and you apply your PGD and you think that, oh, okay, so my robustness is really high. But that's not the case. You can actually break these defenses by just looking at the expectation of these gradients over the randomization that you have. Quite simple. Take the expectation over randomization. So in other words, let's say if your gradient has some randomness, like let's say T is randomness that you have, just look at the expectation over T. If you're dropping out or some nodes or edges, just compute the gradients for many realizations of that randomness, and then just look at the average. And you know, because the gradient is a linear operator, you can take the expectation inside the averaging. So then that's it. Then use that in your attack, and those attacks completely breaks these types of defenses. All right. So in other words, there's a real danger of just relying on these empirical defenses in order to argue that the model is actually robust against the adversarial attacks and adversarial examples. Right. So then the question is, okay, are we always going to have adversarial examples for a given model? Or in other words, are adversarial examples inevitable? So that's the question that we have looked into this problem in this paper with the same title, Are Adversarial Examples Inevitable? I think it is published in ICLR 2019, I believe. So disclaimer, I'm also a co-author on this paper. And here we are basically looking at some theoretical results to understand the cases that we will always have adversarial examples, especially in high dimensional data. All right, so maybe it's a good time to pause and see if there are any questions. So there's a question, this only works for white box attacks, right? Yeah, so as I mentioned in today's lecture and these lectures, we focus mainly on white box attacks. The black box attacks is the case where you don't know the model parameters, and either you do like a model replacement or you do transfer attacks. And most of the times, those types of attacks are pretty successful against black box attacks. And that's why we are focusing on white box attacks in these lectures. What is T of X? T of X is, broadly speaking, the randomness that you introduce to your network, right? So you can maybe say, these are the indicators which edges or nodes I'm dropping out. It's kind of noise, yes. And you can look at different realizations of that in order to compute the gradient and expectation over that. Okay, any other questions? All right, so if not, let's move on. So in this paper, we want to understand some cases, some synthetic cases that we will always have adversarial examples with high probability, right? So it's kind of an important problem to understand these limits and then look at practical points and see if these practical examples, they can be viewed as, some special instances of these results that we show there will always be adversarial examples. So I'll be talking about that at the end of today's lecture. But here we mainly rely on Iso-Parametric Inequalities. Which are really fun inequalities just to know about them in general. I think, they can be useful not only in this problem, but in analysis and other types of problems as well. So that's why I'm going to spend a little bit time to explain what we mean by isoparametric inequalities. All right, so let's look at some notations. Right, so we'll call a sphere a d-dimensional sphere by s d minus 1. If you should mute yourself if you're not speaking to reduce the noise. D minus 1 is the d-dimensional sphere. So basically, these are the set of points in Rd such that the norm, let's say, is 1. So it's a unit sphere. And if we look at the subset on the surface of this sphere, let's say this is my subset A, I'm going to denote by mu of A as the surface area of A. So what is the surface area of a particular subset? So in order to work with just numbers between 0 and 1, we're going to normalize the surface area to the surface area of the entire sphere. Right? So I'm going to basically look at mu of A divided by the surface area of the sphere. And I'll have this normalized surface area, mu1 of A. So now with this mu1 of A is between 0 and 1, right? So if it is 1, it means this set basically is the entire surface of the sphere. If it is half, it means it basically covers half of the sphere. If it is 0, it basically means it is a zero area surface. So it's normalized. It's easier to work with. So this is between 0 and 1. Right, so that's basically our notation about spheres. And we also need to define geodesic distance. Here, basically, if you have 2 points, let's say point x and x prime on the sphere, what is the shortest path between these 2 points on the surface, right? So if you want to travel from x and x prime on the surface of a sphere, so you basically take this curved path from x to x prime. You can take other paths as well, but they are not going to be the shortest. The length of the shortest path between x and x prime on the surface is called the geodesic distance. So this is basically the shortest path, the length of the shortest path between 2 points on a surface. It is not particular for, defined for a sphere, right? So for whatever surface that you have, you can define this geodesic distance. In particular, we have this really nice relationship on sphere. All right, so let me ask you a question. If you look at, let's say, L2, or Euclidean distance between x and x prime, I call it with D2, x and x prime. And if you look at the geodesic distance between x and x prime, which one is going to be higher? Is it shorter to travel x and x prime in a direct L2 path, or on the surface? yes, the geodesic distance is going to be higher, exactly. So we have this really nice result, and we know also L2 is larger than L infinity as well. So it is the same relationship. So by D2, I mean, this is the distance defined using L2 norm. By D infinity, I mean, this is the distance by L infinity norm. By DG, this is the distance, you know, defined by the geodesic distance. It's kind of a simple relationship we have on sphere. All right. So we are going to look at the classification problem. We are going to assume we have C labels. The labels 1 to C. So I show it with the C. These are my number of labels that I have. And we are going to assume each class has a density function. Function denoted by rho C. Right, so this is the true density function that I'm generating samples for each class from. Right? So this has nothing to do with my classifier. This is the ground truth. Let's say we have these density functions. And we assume these density functions are bounded, right? So you don't have an infinite density or like a delta function. These are bounded densities. And we denote by UC the largest density that you can get for a class C. This is the supremum of these densities. Okay? So you can't have a delta function in this definition. You know, density over the surface, right? So density over the space that we consider. So you cannot have a delta function, otherwise, you know, it's gonna, you know, give you a UC of infinity. So we are assuming these densities are bound. Okay, let's look at one more definition. And then we can talk about isoparametric inequalities after this. It's a simple definition. It's called epsilon expansion of a set. Simple by the definition, right? So you give me a set, I'm just gonna like have an epsilon expansion. I'm gonna look at all points that are epsilon close to this set that I have. So I will denote it by A, epsilon, and of course it depends on the distance that we use. It's the set of points that if I look at the distance to a point in my set, the distance is at most epsilon. Or sometimes we are just going to abuse the notation if the distance that we are using is indicated from the context, we are just going to show it with a epsilon. So let's say you have a surface sphere here, and then you're looking at the set on the surface of this sphere, and then the epsilon expansion, basically you're expanding this set by epsilon. Right? So this is going to, if this is your A, this is going to be your A of epsilon when you're using the geodesic distance. All right, so that's about the notations. Let me pause and see if there's any questions. All right, so let's start with looking at probably the most basic isoparametric inequality.
Sorry, can you scroll up a bit?
Yes, just give me a second. Go ahead.
Oh, thanks. I just wanted to see the.
Oh, okay. Good. All right. So let me actually ask you this question before even talking about, you know, these inequalities. Let's say I give you a volume of 1. So, you know, something that you can shape, you know, but like I know like the volume is 1. So what is the, what would be the object that has the smallest surface area? So I can maybe, you know, reshape it. I can, you know, have some other shapes with the same volume. So the volume is 1. And then I can compute the surface area for each of these shapes. Right? So given the volume, I want to identify the shape that has the smallest surface area. What do you think it's gonna be? Yes, that's the sphere, right? So that's kind of, you know, a little bit intuitive, right? Because if you have a sphere with the same volume, if you change the shape, you are kind of, you know, adding surface area to that shape. Right? So that's basically the classical isoparametric inequality, which indicates that of all closed surfaces that enclose a unit volume, the sphere has the smallest surface. Quite intuitive, right? Can you prove it for as a homework? Is it easy to prove? It turns out that this is, although it is very intuitive, but very difficult to prove. In fact, it is, I think there's a good history about this in this classical paper in 78. So it is very intuitive, but not really easy to be proven. Okay, so based on that intuition, we have basically this following simplified result as our first isoparametric inequality. So I believe it is first shown by Levy and Pellegrino in 1951, and later on it is basically simplified by Talleyrand in 1995. So the result is basically saying the following. So it says consider a subset in basically on the surface of a sphere, d-dimensional sphere, such that this subset covers more than half of the sphere. Right? So it's a really big subset. It doesn't have to be, you know, connected. So you may have like some pockets of these subsets in different parts, but it covers at least half of the sphere. And let's say we are basically using the geodesic metric on the sphere, just to measure the distance between the 2 points. In that case, if I look at the epsilon expansion of this subset, so I'm like, you know, I have a subset that covers all, you know, more than half of the sphere. This epsilon expansion is at least as large as the epsilon expansion of a half sphere. So basically it says, you know, it's very intuitive. In fact, let's say you have a subset A on this sphere, let's say maybe like pockets of areas that belongs to this subset. This is my A. Then they look at epsilon expansion of this subset, right? So epsilon expansion would contain all of these points, right? So these are A epsilon. So the surface area of this epsilon expansion is at least as the epsilon expansion of a half sphere. Where you have a half sphere, kind of clean and easy. Right, so that's my A. I just look at the epsilon expansion of this half sphere. So this is the epsilon expansion, A epsilon. Right, so in other words, basically it kind of doesn't matter what is the shape of this set that you consider. There is a lower bound on the size of the epsilon expansion of a half sphere. But the good news is that now we have a good formula for the epsilon expansion of a half sphere. So this formula is by Millman and Schichtman, 1986, that they show for half sphere, if I look at the epsilon expansion of that, it is as large as 1 minus pi over 8, a constant, really doesn't matter, to the power half, e to the power minus d minus 1 over 2 epsilon squared. So that's it. So you give me any shape on the sphere that covers at least half of the surface area. I know the epsilon expansion of that is as large as the epsilon expansion of a half sphere. And I know the epsilon expansion of a half sphere is lower bounded by this quantity that depends on dimension and the epsilon. Okay, so, before I take questions, let's just look at this formula a little bit. Right, let's assume here the dimension is large. D is large. Maybe 10,000, maybe 100,000 if you think about like images and stuff. So we basically look at those types of dimensions. And let's say your epsilon is a number that you have, right? Not even like a big number. So what is the asymptotic behavior of this right-hand side? So we have e to the power minus basically d over epsilon squared. Right, so if d goes to infinity, this term goes to 0, and 1 minus of this term goes to 1. Right, so as d goes to infinity, this whole bound goes to 1. What does it mean? It means in high dimension, if you have a half sphere, you have a surface that covers half of the sphere, and you do just like a very small epsilon expansion of that, it covers almost the entire sphere. It's like one of the things that our intuition that we live in like a low dimensional space, it doesn't carry to a high dimensional world. Right? So in a low dimensional, in 2-3 dimensional space, when you look at a sphere and you say, oh, like, I'll just like do a epsilon expansion of that, even in this picture, you say, okay, so it basically covers, a little bit more than half. But this intuition is not correct So this picture is not correct in high dimension. So in high dimension, effectively speaking, what happens, so let's say D is large. So you have a half sphere, you do an epsilon expansion, and it covers almost the entire sphere. That's one of the really interesting intuitions that we get from isoparametric inequalities. Okay, so we'll see what is the implication of this result in adversarial robustness. But before that, let me pause and take questions. Okay, so there's a question, it goes beyond the sphere. You'll talk about some other shapes as well, like cubes, some other shapes. The sphere one is the most well-studied one. On other shapes like cubes, I'll explain additional difficulties of these isoparametric inequalities. So we don't get like these nice geometric interpretations for them. So here we are just looking at the surface area for the sphere. When I talk about the cubes, we'll also look into the inside. We'll look into the volumes. Okay, so yes, that's correct. Okay, so let's move on. Okay, so now you can immediately see what is the implication of this in adversarial robustness. So we have the following, which is basically following directly, from this observation. Let's say you have a C class classification problem. And then similarly, you have the density rho C with the maximum UC that we discussed. And here we define the VC as, the supremum density relative to the unit density. So it's basically the density of a unit of uniform density times UC. This is max density relative to uniform density, which is like 1 over this number. That's just a simple notation. And here now we basically bring the classifier. We say FC, F sub C, is the area that my classifier classifies as a particular class. So this big C is my classifier. And this is the proportion of my area that is being classified as a particular class C. All right, so the argument here is that pick a particular class, pick your favorite class, that your classifier basically doesn't classify more than half of the sphere for this class, less or equal to 1 over half. So you will always have this, right? So even if you have 2 classes, one class is going to be larger than the other class, at least going to be half, right? So if you have 3 classes, one of them will definitely be, less than half. And then sample a random point from the true density. Sample X from this true density corresponding to this class. Then we argue that 2 events are going to happen. One of these events are going to happen with high probability. Either this point that you're sampling from your true density is going to be misclassified. So it is not going to belong to this set of points that is being classified correctly as label C, or this point is going to have an epsilon adversarial example. So in other words, there will be an adversarial example, epsilon close to this point, on the surface. As I said, this holds with high probability. With one of these events is going to happen with probability 1 minus VC, the normalized density of that class, times basically that lower bound that we had for the isoparametric inequality. This constant times e to the minus power d minus 1 over 2 times epsilon squared. And as I mentioned, as d goes to infinity, this bound goes to 1. So with high probability, if you pick a sample from this class, it is either going to be misclassified or will admit an adversarial example. So in fact, this is kind of trivial, right? So this directly follows from the isoparametric inequality that we had. So let me just briefly show why this result is trivial. Let's say this is my sphere, and let's say R is basically the set of points my classifier classifies as that particular label C. And I know from the assumption that because I know the area of this R, which we call it FC, is less or equal to half, this is not the largest, class in my classification, right? So the area that it has is less or equal to half. So let's look at the complement of this set. Let's call it our complement, the other parts of my sphere. So can I argue that the area of our complement is going to be greater or equal to half? Is that the case? Yes, because R is small, so our complement is going to be at least half. No, basically this R complement satisfies my condition for isoparametric inequality, right? So it's as large as like half a sphere. So if I look at the epsilon expansion of this, I'll just like denote by R complement epsilon, it's going to be a very, very big area. So it's basically in high dimension, it's going to cover the entire sphere that I have. So therefore, if you look at the set of safe points, these are the points that are correctly classified and at least epsilon away from the boundary of this classification. So these are my safe points. By looking at the epsilon expansion of my R complement, the probability of these safe points, so these are my safe points, that none of these two events happen for them, the probability of these safe points is going to be really, really small. So in other words, the complement probability that at least one of those events happen is going to be as large as this number that we have here, which approaches 1 with high probability. Right? So that's basically the proof. Really, really simple, kind of, comes directly from the isoparametric inequality for spheres. Okay, so let me pause and take questions. Amir, go ahead.
So the lemma you mentioned was specifically for the geodesic distance. I suppose that doesn't hold for LPs because they don't respect the, relative curvature of the sphere. I was wondering, since adversarial examples are mostly in LP, could we use this lemma for adversarial examples?
Yes, right. Because as I mentioned, we have this really nice relationship between the geodesic distance and, let's say, L2 distance, right? So if I argue that I am vulnerable against, let's say, an epsilon, perturbation in geodesic distance, then okay, so let's go the other way. Let's say if this is epsilon, right? The geodesic distance is going to be larger than epsilon. Then if I could argue that I will have an adversarial example for epsilon for the geodesic distance, then that will basically, the argument will carry. So even though basically we are using the particular geodesic distance, roughly speaking, the arguments for L2 and L infinity is going to be even worse. Because if you look at L2, converting that to the geodesic distance is going to give you a larger, perturbation budget in the geodesic distance. Make sense?
I see. Yeah.
Good. All right, so let me see if there are other questions. Why is that set on a unit sphere? We are just normalizing it just to for simplicity. All right, so we are normalizing the area to be 1, just to not work with the numbers that can depend on the dimension. Okay, good. But then you can argue, okay, so this was just a warm up, but at the end of the day, we care about images, and images, they don't lie on a sphere. And so the images, if you have an X, which is an image, let's say 1 pixel of this is between 0 and 1, it doesn't lie on a sphere, but you can think about these images to be in a cube, in a d-dimensional cube. So the question is, can we do the same thing? Can we use isoparametric inequalities for cubes to be a little bit closer to practical cases in adversarial examples? So bad news, I have a bad news and a good news. So let me start with the bad news. So the bad news is that geometric isoparametric inequalities don't exist for the cube. Metric isoparametric inequalities don't exist for cubes, right? So the shape that achieves actually the minimum expansion, if it exists, it depends on the volume they enclose, right? So we don't, have this kind of a nice relationship that, okay, so here we know like what is the shape that lower bounds any epsilon expansion. In the cube, it actually, if it exists, it depends on the, the part of the volume that they enclose. So we don't have a nice geometric isoparametric inequalities for that reason. But I have good news for you guys. So the good news is that we can, there are some algebraic isoparametric inequalities exist for the cube, right? So we can have some formulas that bounds the epsilon expansions of volumes in the cube, but we don't have a good geometric view of what is the minimum, what is the best set that achieves the minimum expansion. So let me show one such algebraic isoparametric inequalities. There are many more complicated forms. I'm going to state this, perhaps the simplest one, just to make you familiar with these inequalities. Let's say I have a measurable subset in a cube, in a d-dimensional cube. And again, we are assuming the volume of this subset is at least half. It covers, basically half of the cube. In that case, if I look at the epsilon expansion of this subset with respect to, let's say, P norm, this is at least 1 minus this term, e to the power minus 2 pi, d to the power 1 minus 2 over pi star, epsilon squared. And in the denominator, I have 2 pi epsilon d to the power 1 over half, 1 minus 1 over pi star. And what is pi star? it is minimum between, what is P star? It is minimum between P and 2. Right, so this P is the norm that I'm using here. So let's assume I'm using L2. Right, so let's say for P greater or equal to 2. Right? So let's say I'm using L2 or L infinity, which are like common norms that we use in adversarial robustness. In that case, this formula can actually be further simplified. So the volume of the epsilon expansion with respect to these P norms, P larger than greater equal to 2, is going to be 1 minus e to the power minus 2 pi epsilon squared 2 pi epsilon. Because P star is 2, 1 over half minus 1 over half goes away. So we have this really, really nice simple formula. Right? So you give me any cube in d dimension, and your set A has at least half of the cube. And then you look at the epsilon expansion, let's say with L2, the Euclidean, it will cover at least these this much of volume in the cube. All right, do you see anything weird in this lower bound compared to the previous lower bound? Not weird, anything different asymptotically?
There's an epsilon in the denominator.
That is correct. We have an epsilon here. But where is D? Where is D? Right, so for P less than 2, I have D here, right? And when D goes to infinity, then the rate of the convergence of the numerator to 0 is exponential. So this whole thing is going to go to 0, and then I have 1 minus 0. So this whole thing is going to go to 1 as D goes to infinity when P is less than 2. Right? But for P greater or equal to 2 that we kind of care, I don't see any dependence on D because this goes away. This goes away. All right, so what is going on here? All right, so there can be, couple of things going on. First of all, this is not the tightest bound that we can come up with. Let's consider the case when P is equal to 2, right? It's L2, Euclidean distance that we have, and we are looking at the d-dimensional cube. D-dimensional cube. What is a proper epsilon to use, right? So epsilon is the adversarial perturbation or the epsilon expansion that I have, right? So I'm gonna basically pick an epsilon. Does it make sense to pick a constant epsilon? Does it make sense to say, oh, my epsilon is 0.1, independent of my dimension? So at least for L2, it doesn't, right? Because the diameter of my cube in D dimension is square root of D, right? So my cube in L2 gets bigger and bigger. So if you pick like a constant epsilon, basically asymptotically, this epsilon is 0 because you need to normalize it with your diameter. What are the units of changes in your data? So it kind of makes sense in that case to pick epsilon that is also maybe 0.001 times the square root of these. It's small, but it also grows with the dimension just to make sure that we are not looking asymptotically at the 0 epsilon. And in that case, again, this bound is going to go to 1, right? This bound is going to go to 1, and we are going to observe the same behavior as we discussed for the sphere. Right, so at least for L2, we can see either we are going to have a misclassification or adversarial example with high probability. If we are looking at epsilons that also goes to infinity with this with depending on the diameter of your cube. But now you can argue, okay, that explains for L2. What about L infinity? L infinity is also a popular attack. So in L infinity, what is the diameter of my cube from an L infinity point of view? Is equal to what? So in L2, I know that my diameter is basically square root of d, right? So in L infinity measure, L infinity looks at component-wise differences, right? What are the, pick 2 points that are furthest away from each other in L infinity norm. L infinity looks at component-wise. Yes, it is 1. God bless you. That's the diameter of my cube in an infinity sense. So in this case, it kind of makes sense to pick a constant epsilon, right? So it doesn't have to go to infinity with the square root of d. But then if you use a constant epsilon, this bound is not going to go to 1. So in other words, this isoparametric bound that we have here is loose, is not useful in an L infinity sense in a hypercube. There are better bounds than this that you can use, and you can take a look at the paper. They're a little bit more complicated, so I'm not gonna go into details of them. So using this, you can basically, again, show with high probability, if you pick a random sample, either it's going to be misclassified or will admit an adversarial example with epsilon. All right, so let me pause and see if there are any questions that I haven't answered. Is the one in the pink box in the numerator or outside? Okay, so, oh, good. That was a test to see if you guys are awake. At least one of you is. Good. Thank you, Somek. All right, so let me move on. So far we showed, there are cases that we will, with high probability, we will have adversarial examples. So then what about this question that we ask? Are adversarial examples inevitable in practice? So it's kind of an ill-posed question, in fact. So it is, it is not clear what we mean by adversarial examples to be inevitable, right? Because it depends on, of course, your data distribution. See if it is on a sphere or on a cube or maybe on a manifold of some sort. Images, in fact, they often lives on low-dimensional manifold. We know that from generative models. And in those cases, or at least one of our assumptions that the density should be bounded is not going to hold. But of course, you can add a little bit of a uniform noise and extend some of these arguments. So my point here is that the data distribution is important in order to understand this. Also the threat model. What is the threat model that we consider? We saw, like, at least in the hypercube case, that L2 and L infinity may have different behaviors in terms of these isoparametric inequalities. And something that we didn't actually talk in these results is the hypothesis class. What kind of classifiers are you using in your learning? Right? So we, the results that we had was, fairly general. I didn't even say if it is a neural network or a linear, basically true for any classifier with some conditions that we had on the, the ratio of area that they cover for a particular class. So in other words, in our result, we basically showed there are some distributions and there are some threat models that, yes, indeed, adversarial examples are inevitable. But in practice, we have images that they don't, lie on exactly spheres or cubes. They may lie on low-dimensional manifolds. We have different threat models, LP and non-LP. And more importantly, the question is, can we think about hypothesis classes? Can we think about neural networks with provable or certifiable guarantees against these types of adversarial attacks? And that's something that I'm going to focus on in the next lecture, to see can we have provable defenses against various adversarial attacks.